Okay, this next series of videos is going to go over oscillations. So, if there is a topic that is very much worthy of study in physics, it is oscillations because it's one of those things that tends to come up over and over and over and over and over again. Um, Many phenomena in nature are periodic, which means that the behavior, whatever it is, repeats itself on some sort of regular basis. And so there are two, what I call big ideas that govern oscillations. One is superposition. Um, if you have some sort of complicated oscillatory behavior, it turns out that it can be expressed as a linear combination of simpler behaviors, such as a sinusoidal oscillation. So, within the world of oscillations, getting to really know your friend, the simple harmonic oscillator, well, is very, very important for that reason alone. The other is amplitude independence. Oops, doggone it, independence. What that means is as long as our displacement from the equilibrium position is small, and I'm putting small in quotes here, the period of the oscillation does not depend on the amplitude. Now, the reason I'm putting small in quotes is that if you do push the system far enough, then you'll start to see nonlinearities. Okay, so to build towards developing our simple harmonic oscillator, we want to go and take a look at the linear force. And before we get too far into that, I'll motivate why. So in nature, we have an oscillatory behavior. It's always about some equilibrium position, and we usually define that to be x equals 0, and then our object is out over here somewhere at position x. Oh, man, that looks awful. Let's try that again. Position x. Okay, that looks better. And it'll feel some sort of what we call a restoring force. That is a force that's directed back towards the equilibrium position. So it's attempting to restore it to equilibrium, thus the name. So in general, this restoring force can be some really complicated and annoying thing. But we can go ahead and try to approximate down and see what we can think about. And the first step here would be to go ahead and do a Taylor expansion, or more strictly a Maclaurin expansion, about the equilibrium position. So it'll be equal to some possible constant term, which we'll call f naught, plus we'll have an x df dx evaluated at 0, and then we'll have some higher order terms like 1 over 2 factorial x squared d squared f dx squared plus 1 over 3 factorial x cubed d cubed f dx cubed, plus and so forth. That should be enough. Now, let's sit and think about what we know about these terms. First off, we know that f naught has to be 0. There's a really good reason for that. Let's say it's not. Then at x equals 0, all the other terms have x's in them, and they drop out. And so we would be left with a non-zero force at the equilibrium position, which means there'd be a force pushing it away from equilibrium, which defeats the whole meaning of the word equilibrium. So that's a contradiction, so we can't have that. So we know that in general, our F naught has to be 0. Now, if we pinky swear that our displacement is, again, small, and again, I'm being a little vague about what I mean about small, but we can start to motivate that a bit. Sorry, I forgot to evaluate these at the equilibrium position. There we go. If it's small, then this x squared term, if x is small, then x squared will be really small, and x cubed will be even smaller than that. So we're kind of wishing these away to approximately 0. And so we're left for small displacement that our restoring force is approximately df dx evaluated at the origin times our displacement away from the origin. All right, that's all well and good. Is there anything else that we can say about this df dx evaluated at 0? And yeah, it turns out there is. If I think about this, this has to be negative. And why is that? Well, we want the force to actually take us back to the equilibrium position. So if I'm to the right, x is positive. That means I need the force to be negative. If I'm to the left, x is negative. That means I need the force to be positive. Either way, I need to times x by something negative, and the only game in town is this df dx evaluated at 0. All right, so for simplicity's sake, let's let df dx evaluated at the equilibrium position be set to be negative k. So with that, then our force law becomes f of x equals minus kx. So this is what gets called Hooke's law. Hooke was a contemporary of Newton. He and Newton were both trying to figure out how it was that planets were going around the sun. Newton worked out that's an inverse square law for us, but Hooke was actually playing with this force that scaled directly with distance. Turns out, we'll see later, that he wasn't making a stupid choice. He's sort of making the other choice, but he hadn't gotten to the point of eliminating it yet. Okay, so with that as our background, now we're good to actually start trying to evaluate the simple harmonic oscillator. That'll happen often enough that you'll probably just see me write SHO. Okay, so we can go ahead and write Newton's second law for this. F equals mx double dot. That's going to become minus kx equals mx double dot. Alrighty. So I can get this into more of a standard form. X double dot equals minus k over m times x. Now, it'll be convenient. We'll eventually need to take the square root of this k over m. So let's just call this omega naught squared. That will, then later when we need to take a square root, we'll be good to go. This will actually have a name. We'll call it the angular frequency. Although I haven't motivated that name yet. All right, so with that, oops. So with that, I can rewrite my simple harmonic oscillator as x double dot equals minus omega naught squared omega naught squared times x. Oops, minus sign there. Okay. So, thinking back to our differential equations, you know that the way we solve any differential equations by the time-honored technique of guess and check. You remember that with second-order differential equations where you see a negative like this, a good guess, so our trial solution will be x of t equals, let's say, some arbitrary constant c times the cosine of beta t plus some arbitrary constant d times the sine of, let's call it, gamma t. All right. So then we need to get the second derivative so we can stick it into the differential equation, first to check to see if we're right, and then second to see what constraints we have. All right, so the first derivative, x dot of t, derivative cosine is minus the sine, so we'll have minus beta c sine beta t, derivative sine is cosine, so plus gamma d cosine gamma t, and then take the derivative of that again, so x double dot is derivative sine is cosine, so minus beta squared c sine, cosine of beta t minus, derivative cosine being negative sine, minus gamma squared d cosine gamma t. All right, so let's go and check that, stick the trial solution into our differential equation. So we will have, I'm going to cheat a little bit here, copy, paste, there we go. So we have that part there, that's the x double dot, equal to minus omega naught squared times x. So that's going to give me a minus omega naught squared c cosine beta t, minus omega naught squared d sine gamma t. Alrighty. So we put this together, we see that first off, the only way this is going to work is if both from the multiplier side here, we need at the very least that beta be plus or minus omega naught, so that I'll have an omega naught squared here and an omega naught squared there, so that that equality works out. But then we also have to take a look at it and realize that in order for the cosine, that should be reading sine there. My bad. But also, in order for the sine function to work out, we're also going to need it to be equal to the positive branch. So this forces beta to equal gamma to equal omega naught. All right. So that's good. So if we go back to our trial solution, we'll call that star for the moment. Now that we've determined that the beta and the gamma are equal to omega naught, we remember that in general something like this can be rewritten. So we can rewrite our x of t as just some single constant a times the sine of our omega naught, which is both our gamma and our beta here, omega naught t, plus some phi naught. Okay. So now we have to identify what the a and the phi naught would be. Okay, taking a look at that. To get our, so we'll rewrite our trial solution here. So x of t, if we put into the trial solution, this will become some a sine phi naught cosine. So here what I'm doing is I'm using trig identity from here. A sine phi naught cosine omega naught t. There'll be plus a cosine phi naught sine omega naught t. All right. So if we look back to what we had before in the trial solution, this bit here, just this much of it has to be my c, and that much of it there has to be my d. All right. So this gives me my phi naught, because what I can do is I can divide c by d. So if I divide c by d, c over d equals, I'll have an a sine phi naught over a cosine phi naught. A's cancel, and I'm left with the tangent of phi naught. Cool. So tangent of phi naught is equal to c over d, and we usually call that the initial phase. It gets that name because at time 0, our initial conditions, that will set the initial position and the initial velocity of the object. Okay. Similarly, to try to get a constraint on our a, if we add c squared plus d squared together, that'll make the sines and cosines go away to something we understand. That'll become a squared sine squared phi naught plus a squared cosine squared phi naught. We recognize the sine squared plus cosine squared is equal to unity, so we just get a squared. So we have that a squared is equal to c squared plus d squared. And we call a the amplitude. And we interpret this, if we go back looking at our nicely rewritten solution right here. So we interpret the a as how far away from equilibrium on either side the object ever gets during its oscillatory motion. Okay. So continuing to use that form of it there. So I'll just rewrite it here real quick. X of t equals a sine omega naught t plus phi naught. The argument of this right here, of the sine, gets just called the phase. So the initial phase then is when t is equal to 0, and leaves you just the phi naught part. Okay, so we can plot some sort of typical oscillation, keeping in mind, so we're going to get Here I chose initial phase where phi naught was equal to pi over 2. So so if this is the time here, this much time right here to where our sine function would have begun, that's going to be equal to phi naught over omega naught. Okay, this is plus a up there, minus a down there. Okay, the time between two identical successive features is called the period, t naught. Yeah. So we realize that what this is that when one period has elapsed, we think about this, to get the same identical feature back, our phase will have had to increase by 2 pi. So this is going to require that my omega naught times t plus t naught plus my initial phase. So that's the argument one period later. I subtract from that my initial argument, omega naught t plus phi naught. Okay, so here we have cancel, cancel, and here we have cancel, cancel there, and that has to be equal to 2 pi. So we can interpret, so we get that the period is equal to 2 pi over the angular frequency. Now we can get to why we call it the angular frequency. Since this is the number of seconds per oscillation, number of oscillations per second, the period, the frequency, f naught, we define that to be 1 over the period, and from what we just got from before, that yields that the angular frequency is equal to 2 pi times the frequency. Okay, so let's start with a more familiar problem, and we'll do it 2 ways. Let's start with doing the simple pendulum. Alright, so I've got a ceiling here, I attach to it a string, pull the bob off to one side there, strings of length L. We'll say the mass of the bob is M. So here's my equilibrium position there. We'll say that we're an angle theta off to one side, and we'll call this arc length there S. Okay. So if I draw a free body diagram for the mass, got the tension pointing up the string, and I have gravity pointing down. There. Alrighty. The natural choice of coordinate system, well, let's go with a thinner line there, shall we? The natural choice of coordinate system is going to be directed in towards the attachment point to the pendulum here. So that makes the portion of gravity that's attempting to restore to equilibrium right there equal to mg sine theta. Sorry, with a minus sign, because if we're to the right, the sign is positive, and we need that to point to the left, and so forth. So I can write the Newton's second law then, ms double dot will be equal to minus mg sine theta, but s is equal to L theta, so I can write that as ml theta double dot equals minus mg sine theta. Cancel, cancel. So we get that it doesn't matter what the mass of our bob is. So theta double dot is equal to minus g over L sine theta. And that is as far as you probably want to take it. Eventually we'll drill down into this a little better, and we'll get that the answer to this thing is an incomplete elliptic integral of the first kind. The existence of a first kind, of course, implies the second kind, and the existence of incomplete implies the existence of complete. Let's just say they're nasty. But again, we're all about trying to get to things that we know how to solve a little better. So we can, once again, remember our Taylor expansion for sine theta. It is equal to theta minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the fifth minus plus da da da. Okay. So now, once again, we're going to demand that theta equals small. In this case, that works out to be about 20 degrees or so. So if we let theta be equal to small, then theta cubed is really small. Theta to the fifth is even smaller than that. And as long as we're working in radians, we can approximate sine theta with theta itself. So now going with that, we can go back to our original equation for the pendulum here, star. And so now star becomes something I can actually handle. It'll become theta double dot equals minus g over L times theta itself. And that fits the pattern of our simple harmonic oscillator. Second derivative of stuff equals the negative of crap times stuff. And we identify the crap as omega naught squared. So we can get that, we get that omega naught is equal to root g over L. And that will give us that the period is 2 pi, period is 2 pi root L over G. Okay, so that's one brush with the pendulum. Now I'm going to do what seems to be a different problem, but just to show that you should get in the habit of when you see something that winds up looking like something you've seen before, that you should recognize that you've found the answer and then just start going from there. So in this example here, we're going to look at a bottle in a bucket. So there's my bucket. There's some water, like so. I'm going to attempt to draw a bottle. You know it's a bottle because I told you it's a bottle. There we go. So there's my bottle, and we'll fill some part of it. And the water line here will be below the water line there because we've got the weight of the glass as well. So let's go ahead and call the equilibrium depth right here. We'll call that equilibrium depth d naught. Okay. Now, let's say that I go ahead and just give this a little push. Down like that, and so then the bottle there. So my new depth will have increased by some extra distance x. All right. So we can go ahead and write Archimedes' law for this. So mx double dot equals the buoyant, equals gravity pulling down, mg, and the buoyant force is trying to push it up. So we'll say minus, so I'm choosing down positive here, minus rho g a, where a is the cross-sectional area of the bottle, times the bit below the waterline, d naught plus x. Okay. Now, we can separate this out into two bits. We'll have mg, let's distribute this across, minus rho g a d naught minus rho g a x. And I submit that these cancel, because if we're at the equilibrium depth, the forces are equal, right? So those two there cancel. And so we're just left with mx double dot equals minus rho g a x. Well, okay. So we get that x double dot is minus rho g a over m times x. So second derivative stuff equals minus crap times stuff, and the crap, this bit right here, we identify as omega naught squared. So we have the angular frequency being root rho g a over m. But remember this bit that I canceled here. These two terms are equal, right? So m has to equal rho a over d naught. So we'll just point that out. M equals rho a over d naught. So now I'll stick that into there. So omega naught is root rho g a over rho a over d naught. Doesn't matter what the fluid is, does not matter the cross section of the water bottle. It is root g over d naught. Well, you know, it's a pendulum too. Now, this should be feeling a little different about this, because you realize that, wait a minute, we had a constant force here. We had, in this case, the force of gravity. But all that does is shift the equilibrium position. It doesn't change the angular frequency. So we could do another example of that that's maybe a little more familiar, just to show how that goes. So let's say that I have some spring here and got mass on there, and this length here we'll call the equilibrium length, capital X sub E. All right. Now, let's go and instead hang this vertically. So if this distance here was my old XE, if I just hang it and let it sit, that new distance there, we'll call it XE prime. That's my new equilibrium position. And then, if I go ahead and displace it off of this new equilibrium position, we will displace some distance, little x, away from the new equilibrium position. And we'll go ahead, just for completeness sake, we'll call that total length, like so, just capital X. All right, so that seems like a lot, but again, let's go ahead and do Newton's second law on this. So we've got the force of gravity acting down, mg, minus, and we've got the spring acting up. Well, how much is the spring stretched by here in the new equilibrium position? So we'll start with that much. It'll have been stretched by xe prime minus xe. That equals mx double dot, but since that's equilibrium, that's equal to 0. So what we get is if we ever run across, and we will, if we ever run across a k xe prime minus xe, we can just replace that with mg. Okay, so we're all good there. Or if I prefer, I can take that one step further, and I can rewrite my xe prime as xe plus mg over k. All right. So now let's think about what my little x is. My little x is just my big X minus xe prime. But that would be the same difference as x minus xe without the prime minus the mg over k. Okay. So now, for my equation of motion, when we're not in equilibrium, whoops, what did I do? Okay, so for my equation of motion, when we are not in equilibrium, the total stretch of the spring isn't little x. It's going to be big X minus xe without the prime. So we'll have mg minus k, big X minus xe, and that equals mx double dot, and that just stays like that. Okay, but we can go ahead and wherever we see an x minus xe right here, we can rewrite that as little x plus this mg over k. So that's what we'll do. So we have mg minus k times little x plus mg over k. Hey, k times k is mg minus, that cancels. And that equals mx double dot. And so then finally, I get to x double dot equals minus k over m times x, or we can then say that that's minus omega naught squared x, identifying omega naught as root k over m as before. So the upshot between doing is that if we do have some sort of constant force acting on our object, like say gravity, all it does is shift the equilibrium position. It doesn't shift the it doesn't change the natural frequency. Okay, in the next video, we'll take a start at looking at the energy considerations of a simple harmonic oscillator.